Good afternoon, everyone. So for me, it's a great pleasure to introduce Professor Marcos Pimenta from Unesp in Presidente Prudente in Brazil. Marcos Pimenta is an expert on variational method for elliptic PDEs. And today we have the great pleasure to listen him to talk about existence of a BV solution for a mean curvature equation. So Marcos, thank you very much for accepting our invitation, and you have the word.
Okay, thank you very much, Professor Diego, and also Professor Juan Limico, by the kind invitation. For me, it is a great pleasure to have this opportunity to tell you a little bit about a work which we have done in a joint work with Professor Marcelo Montenegro from the University of Campinas in Brazil. And it tells about something that in which I have been interested in the last 4 years, more or less, okay? Okay, then let me introduce you to the topic I would like to talk about. Okay, I would like to talk about a problem involving the mean curvature operator, okay? And then it is an elliptic PDE in which we would like to use variational methods to deal with this sort of problem, okay? I think that for everyone which already have dealt with this sort of operator, probably knows that it is very difficult to deal with it because it is an operator which presents different degrees of homogeneity in the region, because in the region, near the region, this operator behaves like the usual Laplacian operator, okay? Rather, near the infinity, this operator looks like the one Laplacian operator, okay? Then it have an asymptotically linear growth, but it is a nonlinear operator, okay? Then it is very difficult to deal with it, even when we try to use very common variational methods to it. In general, we have some sort of problem when trying to doing so, okay? Okay, let me show you what some of the approaches that the people have used in the last year to deal with this sort of problem, okay? Okay, then the first one that I would like to show you, it is by dealing with this operator looking for radial solution, okay? Then what our people are used to do is to consider a function u as a function of the modulus of x, okay, in the sense that it is a radial function. And then, of course, dealing with the associated problem, okay? If we do it, the associated problem is going to be ordinary differential equation. Then, of course, it is much more easy to deal with it than with the original problem. And of course, an advantage to deal with this equation by this method is the gain of compactness that we have since we pass to deal with it in a Sobolev space, which is defined in the real line, okay? But of course, the disadvantage that we have in dealing with this sort of problem is that through this approach, we cannot get a solution which is not a radial solution, okay? Then, of course, this method, it just gives rise to radial solutions. For example, in this paper, they have used this method to deal with a problem in a ball, okay, with a radius big enough, and then they use some information of existence and non-existence of solutions of related problems to get a solution to this problem in all of the Rn, okay? Okay, let me show you now another possibility to deal with this problem. It is through the elliptic regularization. What the people are using to do is to sum a regular R Laplacian operator to the problem, okay? Then, of course, this operator right here, it is dominant with respect to this one, as far as variational methods are concerned, in such a way that you can deal with this sort of problem in the usual Sobolev space W1R, okay? And then, of course, since we are looking for a solution of this problem, which involves just the mean curvature operator, we put here a parameter epsilon, which we are going to go. We are going to analyze this problem as epsilon goes to 0. Okay. Okay. Then, by dealing with this sort of problem, with this sort of approach, we must solve the problem which the R Laplacian summed to the main operator. Then we have to get some kind of estimates to this problem which are uniform with respect to epsilon, and then we make epsilon goes to 0. Okay, and then we try to get some kind of limit of this sequence of solutions, and then this limit is going to be the candidate to be the solution of the original problem. Okay. Then, for example, in this paper from Professor, two Italian guys, which is Pier Paolo Mari and Franco Bersnen, they have studied this sort of problem. Okay, through this approach. And also in this operator from Denis Bonner and some other collaborators, they have studied more or less the same problem, which has slightly different approach, okay, but a very, very, very nice work also. Okay, the last approach that I would like to show you, to present to you, is a truncation argument. Okay, it is based on considering a similar problem, but substituting the main operator by something which is equal to the main operator as the argument of the function a, it is small enough, okay? But in such a way that if the argument of the function a, it is greater than some specific value, then this function does not grow as it will be, which the mean curvature operator, okay? In such a way that this elliptic problem here, it is much easier to deal than with the original one, because this function a here, it is much well behaved as we will be in the original mean curvature operator, okay? Then the main advantage to deal with this problem through this argument is that we can deal with it in the usual Sobolev space H10, okay, which makes the application of the technique much easier. But of course, we must, in order to recover a solution of the original problem, we must have that the L infinity norm of the gradient of the solution, it must be less than a positive value, which is predefined before, okay? Then of course, we cannot use this method to give rise to solutions which a high L infinity norm of the gradient of U, okay? Then of course, it is a very strong disadvantage to this sort of method, okay? Okay, now what I would like to show you now, it is a different approach to deal with this sort of problem that, up to my knowledge, it have been developed by the very first way in our paper together with Professor Marcelo Montenegro, okay? And the inspiration to do it, we have taken from a very known argument which is used to deal with one Laplacian problems, okay? Okay, as far as one Laplacian operator is concerned, there are mainly two possible approaches to deal with it. We can either deal with it by dealing with the energy function of associated to the problem directly in the natural space of functions to deal with it, which is the space of functions of bounded variation, the space BV, okay? But we can also deal with this sort of problem through an approximation scheme in which we consider P Laplacian problems, okay? In the nonlinearity, we just repeat what we have in the original problem. Then we solve this sort of problem and then we try to recover a solution of the original problem, okay? This method, this approach have been developed by some Spanish mathematician, also by a French mathematician, which is Professor François de Menguel, and also Professor José Masson, Fouet Saint-Andreu, Balestri, Vicente Caseles, in which in the early 2000s, they have developed this approach to deal with this sort of problem, okay? Then the procedure consists in deal with the approximated problem, then to solve the approximated problem, which is much more easy because we can deal with it in the usual Sobolev space W1P, okay? Then we must get some uniform estimates to this family of solutions with respect to the norm in the space in which we should deal with the one Laplacian problem, which is the space of functions of bounded variation, the space BV, okay? And then once we get this sort of estimate to this to the BV norm of the functions UP, we can get a limit in the topology of the usual Lebesgue space to this family UP, okay? Then we get a function U, which is the candidate to be the solution of the original problem. And then we can also use the estimates that we have got to get a weak limit to the vector field, which is inside of the divergence of the problem that we are using to approximate the original one, okay? Then, roughly speaking, what we should do is to get an estimate which allows you to get the weak limit of this vector field right here, okay? Then we can get a vector field Z, which is the weak limit of this vector field right here. And now what we must do is to show that the function U that we have got, and also the vector field Z that we have got, both of them are linked together through some conditions which tell us that the vector field Z plays the role of what we have inside of the divergence of the original problem, okay? Then we can show in a very easy way in general, then the vector field Z and the function U, it does satisfy the original equation in the sense of the distributions, but we must show that the vector field Z and the function U are linked together in a way that we can say that the vector field Z plays the role of what we have inside of the divergence of the original problem, okay? Then we must have a condition that says to us that Z plays the role of the gradient of U be divided by the modulus of gradient of U, okay? But the very first thing that we should observe is that since the function U, it is just a function in the space of functions of bounded variation, the derivative of it is just a distribution which is generated by a random measure, okay? We don't know if the gradient of U, it is a distribution generated by an L1 function. This is a very big problem because we cannot, for example, say that the inner product between Z and the gradient of U, it is equal to something, because this object here, it cannot be well defined if the gradient of U, it is a measure instead of L1 function, okay? Then what we should do is to use a sort of generalization of this inner product, which is contained in the pairing theory from Gabriele and Zelotti, which have been developed in the 70s and in the 80s, okay, by an Italian mathematician. And then what we should prove is that I would call it here the generalized inner product, okay? The generalized inner product between Z and the gradient of U, it is equal to the total variation of the measure du, okay? In a sense that if we know a little bit more about U, about the regularity of U, okay? And if we know that U, it does belongs to W11 in such a way that the gradient of U, it is really an L1 function, then the inner product between z and the gradient of u, it will be equal to the modulus of gradient of u in such a way that we can say that z plays the role of the gradient of u divided by the modulus of gradient of u. Okay? Very good. This is just about one Laplacian problems. And what we would like to do is to repeat the same kind of procedure, but now apply it to a different operator, which is the mean curvature operator. Okay? Okay. Then in a joint work with Professor Marcelo Montenegro, we have used a similar approach to deal with this problem right here, okay? In which we have put it in the right-hand side of the problem a very trivial and easy geometry in the function f, because we would like to isolate the problem, isolate all the difficulties which comes from the operator and not from the nonlinearity, okay? And what we have done is we have approximated this problem right here through this quasi-linear elliptic problem, okay, which can be treated in the usual Sobolev space W1P instead of the BV, which is the natural function space to deal with problems involving asymptotically linear operators, like, for example, the mean curvature operator, okay? I mean, this is the problem 8, it is much easier to deal with it than the problem 7, okay? Then we solve the problem 8, we get a solution UP, we must show that there is an independent estimate on the BV norm of the UP, okay, with respect to P, in such a way that we are able to get a function U, which is the limit of, in the usual Lebesgue space of the family UP. And also we can use this estimate right here to show that this vector field, this family of vector fields right here, that we can realize that it is in fact inside of the divergence of the approximated problem, it does converge weakly to some vector field Z, which we must establish a condition which links together the vector field Z and the function U in such a way that this condition says to us that the vector field Z plays the role of what we have inside of the divergence, okay, of the usual mean curvature problem. And this is roughly speaking what we have done in this problem, okay? Then we succeed in showing that the vector field Z that we have got and also the function U, it does satisfy this problem, this equation right here in the sense of distribution. And now we would like to, we should show a condition linking together the vector field Z and the function U in such a way that it ensures that the vector field Z plays the role of this expression right here, okay? Okay, then let me, before I present properly the condition that we have found, I would like to introduce you a little bit of convex analysis, which in some sense have a link into the last talk of Professor Américo Cunha, which have talked about optimization right here, okay? I'm not an expert in optimization and even in convex analysis at all, okay? I just have studied enough to develop the approach that we have used in the problem, okay, in the paper. Okay, then let us suppose that G, it is a convex function from Rn in the extended real line, okay? Then we can define the function G star, we can call it the convex conjugate of G, which is defined through this expression right here, okay? Then it can be proven that the function G star, it is also convex, and it is it is very closely linked with the function G through an inequality which is called the Young-Fenshaw inequality, which is an inequality which, roughly speaking, generalizes the usual Young inequality that everybody knows when we study functional analysis, okay? Then we have the Young-Fenshaw inequality between G and G star in such a way that for every pair of vector fields in Rn, the inner product between X and X star is less than or equal to G applied to X plus G star applied to X star, okay? If we know a little bit more then, for example, the function g, it is a C1 function, then by the very definition of the function g star, we can see that the equality right here, it is satisfied if and only if if and only if at a vector if x star it is a vector in Rn in such a way that x it is equal to the gradient of g applied in x star. Okay, I mean the equality 11 it is satisfied if and only if x star it is equal to x star is such that x it is equal to the gradient of g applied in x star. Okay, very good. Then we can, okay, now let us apply this inequality, this fact that I already have told you, to the function g, which is a convex function, which is the square root of 1 plus modulus of x squared, okay? It can be proved that the convex conjugate of g, it is equal to this expression right here, minus the square root of 1 minus modulus of x squared, okay? In such a way that the gradient of g applied in x it is equal to this expression right here. And then what we know is that by applying to this expression the function g and the function g star that we have shown, we know that x star it is equal to the gradient of g applied in x if and only if the inner product between x and x star it is equal to g applied in x plus g star applied in x star, okay? Then we can see that the x star it is equal to this, which is related to what we have inside of the divergence of the mean curvature operator, if and only if we have satisfied this equality right here, okay? Now, if we apply this very fact when we have, for example, let us get a function u in W11, let us get a vector field z, such a way that the L infinity norm of it is less than or equal to 1, then we can claim that z, it is equal to the gradient of u divided by the square root of 1 plus modulus of gradient of u squared, if and only if the inner product between z and the gradient of u, it is equal to this expression right here, okay? And look at what we have in the right-hand side of 14, it is exactly what we have inside of the divergence of the mean curvature operator, okay? Then we have found an expression which is an equivalent proposition which tells to us that the vector field z, it is exactly what we have inside of the mean curvature inside of the divergence of the mean curvature operator, okay? Of course, this just works when we have a function u which does belongs to the W11. But here we have a problem, because when we solve problems involving the mean curvature operator, what we should expect is to get a solution in the space of function of bounded variation, which is a spacer which is wider than the space W11, okay? Then of course, if we have u a function in BV, we don't know that these expressions, it is well defined, because we have, roughly speaking, two problems. The first one, it is that the gradient of u, it is just a measure, a random measure. Then we have not well defined what we have on the left-hand side of this expression. And even what we have on the right-hand side of this expression, it is not well defined as well, because the gradient of u, it is just a measure. Then with this expression does not make sense, okay? Then what we should do is to generalize all of these objects in this expression that are not well defined when we have a function in the BV, okay? Very good. Then taking this expression right here into account, and taking also into account the generalizations of these objects that I have quoted, to the usual inner product, we already have a generalization to it, which is given by the pairing theory from Gabrieli and Zelotti, okay? This object right here, we can generalize to the world of measures in a very straightforward way, okay? It is very known. And this expression right here, it is well defined because Z, it is a real vector field in such a way that this expression, it is well defined, okay? Then, taking all of this into account, in our work, we have defined a sense to a solution to a problem involving a mean curvature problem, okay? In the sense that a function u in the space of functions of bounded variations is going to be considered as a solution to this problem if and only if there exists a vector field z in such a way that the infinity norm of it is less than or equal to 1, in such a way that the minus divergence of z, it is equal to the f of xu in the sense of distributions, then it is a very, very weak formulation to the problem, okay? And we have this condition right here, which in such a way that what we have in the left-hand side, it generalizes what we have in the left-hand side right here, and what we have in the right-hand side is what generalize what we have in the right-hand side right here, okay? Then this condition, roughly speaking, says to us that the vector field z plays the role of what we have inside of the divergence of the mean curvature operator, okay? And also we have a condition which it is a little bit technical and very difficult to explain, but it is something which is linked with the boundary conditions. And in this problem, it is the maximum that we can expect to a BV solution, okay? We just should expect a little bit more if we have more regularity about the function u, what in general we can get in general, okay? Then a solution for us is going to be a function u in BV such that it admits a vector field z in such a way that all of these three conditions are satisfied, okay? Okay, now I would like to show to you a little bit more about the details. I think that I should skip the calculations because I will not have enough time to show off all of them. But I would like to show at least the main ones that makes the problem, the paper, the work, in my opinion, a little bit relevant. Okay. Okay, then in 13, the paper from myself and Professor Marcelo Montenegro, we have studied this problem right here. The condition in F, it is, I would like to skip the condition, but roughly speaking says to us that the energy function associated to the problem is going to be coercive, okay? In such a way that the geometric aspects of the energy functional is going to be as easy as possible, okay? Then we have these conditions right here that, roughly speaking, says to us that F, it behaves as something which is sublinear with respect to the main part of the energy functional, okay, the original energy functional. And our theorem says to us that if we have all the conditions be satisfied, then we have a parameter lambda star in such a way that for lambda less than lambda star, the original problem admits a BV solution, which is non-trivial, okay? Okay, then the first step is to prove some lower semi-continuity of some functionals which appears in the middle of the calculations, okay? Then we should first of all show that the function from BV into the R, which takes U and maps to this expression right here, it is semi-continuous with respect to the L1 convergence in such a way that if UP, it is a sequence which converges to U in L1, then this expression right here, it is less than or equal to this expression right here, when phi, it is just a test function, okay? This is very easy to prove, in fact, okay? It comes from the fact that the integrand, it is convex, okay? Then it is, roughly speaking, weakly lower semi-continuous, and then we can prove this lemma right here, okay? Now we arrive at the very core of the work, which is the lemma 2.2, that unfortunately in the original work from myself and Professor Marcelo Montenegro, it is not correctly proved, okay? There is a mistake right there, but we knows how to correct it, and I would like to present you the corrected version of this of this proof, okay? And the proof, in fact, it has been done by Professor Claudio Alves and some collaborator, which gets some inspiration from papers of Scheven and Schmidt, which is two German mathematicians, which also have dealt with problems involving the mean curvature operator, okay? And then, okay, then this lemma, it is a little bit technical, but is going to appear in a crucial part of the paper, okay? Then let us consider that we have a sequence UP in such a way that the UP does belongs to W1P, okay? Such that the LP energy of UP, it is uniformly bounded with respect to C, okay? It is uniformly bounded by C with respect to P, okay? Then there exists a function u in BV, which is the limit of UP in the space L1. And also there exists a vector field Z, which has some kind of regularity, and this is put it in the sense that Z does belong to some specific sets of vector fields in such a way that the divergence of it is a function which belongs to Ln, okay? This is what we mean, Z belongs to Xn, okay? In such a way that the gradient of u divided by this expression, it weakly converges to z in the space L1, and the main part of the lemma is that this expression on the left-hand side, which it is similar to what we have in the condition of the equation that says to us that z plays the role of what we have inside of the divergence of the mean curvature operator, it is less than or equal to the limit of sp covers to 1 to this expression right here, okay? It is a very hard task to prove this problem, okay? To prove this lemma, it is really difficult. But the correct proof, I would like to show just the sketch of the proof, okay? It is possible to show that since we have this estimate right here, then this family of vector fields, it is bounded in L1 and also equiintegrable, okay? And then we can use some standard arguments from functional analysis to find a vector field Z in L1, which is the weakly limit in L1 of this family of vector fields, okay? And it is also easy to prove that the L infinity norm of Z, it is less than or equal to 1, okay? A little bit technical, but not so much difficult. Okay, now we can apply Young, the usual Young inequality in order to get estimate to the L1 energy of the gradient of UP, okay? To an L1 norm to the gradient of UP. Then we can just use the usual compactness the compactness of the embedding of BV into the L1 in such a way that there exists a function U, which is the weak limit of UP in all the Lebesgue spaces between 1 and the critical exponent to the embeddings of the BV, which is the n divided by n minus 1, okay? And now we start to put a flavor of the convex analysis that we have shown a little bit some minutes ago, okay? Then we consider a function GP, which is equal to this expression right here, in such a way that the gradient of it is going to be something which is related to this expression right here, okay? Then we present a function GP, which is given by this expression right here, and then it is a convex function. It admits a convex conjugate. We have the Young function inequality putting together GP and the GP star, okay? And we know that the equality of this expression it is satisfied if and only if the vector field, the vector x star, it is equal to the gradient of GP of x, okay? Very good. Then by denoting the vector field ZP by the gradient of GP applied in the gradient of UP, which is going to give us exactly this expression right here, okay? Then this expression right here is what we have exactly in this right-hand side, which is right here, okay? Then what we have here is the product, the inner product between the gradient of u, p, and the zp. It is going to give us exactly this thing right here. This is equal to this expression right here, I mean gp, or this expression, plus the gp star, it is given right here, okay? Then we multiply both sides by phi, a test function, and we integrate both sides, okay? There is just a mistake right here. This test function here must be taken to be non-negative, okay? It must be taken to be non-negative. Okay, then we have this equality right here, which comes from the equality in the Young function inequality involving the functions gp, okay? Okay, another well-known fact is that this family of functions gp star, it has some kind of monotonicity in such a way that if r is less than or equal to s, then the gs star, it is less than or equal to gr star, okay? And also the functions gr star, when r converges to 1, it does converge to the convex conjugate of the function g1, okay? Which is exactly what gives rise to the mean curvature operator. And it is possible to show that the g1 star, it is given by this expression right here, okay? Okay, then what we do is the following. We fix an epsilon positive, then we take p less between 1 and 1 plus epsilon, and looks that we want to analyze the expression as p converges to 1, okay? Then, of course, we can take p small enough in such a way that this holds true, okay? Then by the monotonicity of the function gp star, here it must be gp star, okay? There is a misprint right here. This must be gp star of zp, it is greater than or equal to g1 plus epsilon star of zp, okay? Since g1 plus epsilon star, it is convex, then it is weakly lower semi-continuous with respect to L1, in such a way that if we take both sides of this expression, the limit as p converges to 1, what we have in the left-hand side, it is this expression. What we have in the right-hand side is going to have from below this bound right here, okay? The integral of phi multiplied by g1 plus epsilon star applied in z, okay? And now what we should do is to make epsilon goes to 0, okay? If we make epsilon goes to 0, the left-hand side does not depend on epsilon. What we have in the right-hand side, it does depend on epsilon, but it does converge to this expression right here. Then what we get in the right-hand side, it is this expression right here, okay? Then calculating the limit as p converges to 1 in this equality right here, what we have in the left-hand side, it is equal to this, okay? And what we have in the right-hand side is we have just calculated the limit as p converges to 1 of this expression right here, okay? We know how to calculate this expression, the limit as p converges to 1 to this expression right here, because we already have done it before of this lemma. And then what we get, it is exactly this expression right here, okay? I mean, we succeed in proving that there exists a vector field z, there exists a function u, in such a way that the limit of this expression, it is greater than or equal to the sum of these two objects right here, okay? I know that this is very abstract. In the first glance, in the first look, it doesn't seem to be something related to the original problem, but in some minutes we will see together how we can use, in fact, this lemma. And you are going to believe me when I say that this is the core of the argument, okay? Okay, now we should start to proving the main theorem, because all that we have done until now, it is just technical problems, technical lemmas, okay? Okay, then the problem, the approximated problem is going to be this one. The weak formulation of this, a weak solution to this It is a function u in W1P0 of omega in such a way that it is satisfied for all v in W1P0, okay? We know how to deal with this sort of problem because it is a general problem which have been tackled on by several mathematicians, okay? Because it is very easy to find papers in which they deal with even general problems than this one, okay, with a phi Laplacian operator right here, okay? Then the energy function associated to this problem, it is given by this expression, okay? It is possible to show that this energy function, it is coercive, it is bounded from below, and it does have a global minimum, okay? I have some calculations right here. It is just by using the growth condition on the nonlinearity f, then we should use Young inequality, Holder inequality, then some Sobolev embeddings in such a way that we can easily show that GP it is really a coercive energy functional and also bounded from below, okay? In such a way that the infimum, the global infimum of this functional, it is well defined, okay? Then we just take a minimizing sequence. It is, of course, a bounded sequence since our energy functional, it is coercive. Then we can get a weak limit in the space W1P, okay? And then, of course, this UP is going to be the candidate to be the solution, and we can just use some properties of semi-continuity of the some parts of the operator, and also the growth condition on F in order to show that UP, it is a global minimum of this operator right here, okay? Of this functional right here. I must say that the energy functional J, it can be, in fact, a non-differentiable operator because the conditions that we have put to F, it allows F to be a singular nonlinearity, okay? But even so, we can apply some different arguments, okay? Very technical arguments, for example, from Su Nijing, which is a Chinese mathematician which have dealt a lot with problems involving singular nonlinearities in such a way that we can, even in the situation in which JP, it is not a smooth energy functional, we can show that UP, it is a weak solution to the problem, okay? Then we can say that UP, it is a weak solution to the problem, okay? Very good. Then the next lemma, it says to us that there exists a p bar greater than 1 in also a lambda star in such a way that for lambda greater than lambda star and p between 1 and p bar, UP, it is a non-trivial solution, okay? It have to do with the condition that we have put it into F in such a way that we can show that the energy of UP, it is less than the energy of the trivial solution, okay? Okay, now I have 9 minutes by my clock right here. And okay, now what we should do is to show that the sequence UP that we have got of solutions to the approximated problem, it is really a bounded function, a bounded family in the space of functional bounded variation, okay? In order to do so, we must apply some arguments that I will skip right here, okay? But it have been made by Alexis Molino from Spain, from Almeria, and from Sergio Segura de Leon from the University of Valencia, okay? In which they by using these kind of arguments, we can show that the sequence UP, it is bounded in BV, okay? Okay, I have put it here, the arguments, but I think that I must skip, okay? Then from the last lemma, we know that there exists a function in BV, which is the strong limit of UP with respect to the usual LR topology, okay? Then we know that there exists a U, which is a function in BV, which is the limit of UP in the space, usual Lebesgue space for all R between 1 and 1 star, okay? Okay, we can also use the kind of estimate that we have got in order to show that the family of vector fields that we have inside of the divergence of the approximated problem, it weakly converges to a vector field Z in the space of functions of L1 in such a way, okay, we know that there exists a Z such that a vector field Z such that the L infinity norm of it is less than or equal to 1, which is the weak limit of this family of vector fields right here, okay? And it is not difficult by using this convergence that I have cited above, that the vector field Z and the function U, it is linked together because they satisfy the equation minus divergence of Z equals to lambda f of xu in the sense of distributions, okay? This is the easiest parts of the argument. And to be honest, the toughest part of the argument is to show that the vector field Z and the function U are linked together by the condition that we have found that we already knows that it implies that Z plays the role of gradient of U divided by the square root of 1 plus modulus of gradient of U squared, which is exactly this expression right here, okay? Then we must show that Z and U, it does satisfy this equality right here, okay? Okay, what we have in the left-hand side, it is something which generalizes the usual inner product, okay? And this, it can be defined as a distribution, and it can be shown that it is this distribution, it is generated by a measure, okay? And since we know that the infinity norm of Z, it is less than or equal to 1, it is possible to show that this measure, it is less than or equal to this expression that we have on the right-hand side, which is still a measure, okay? Then we should show that this equality, it holds in the sense of the Rabin measures. Then it is enough to show that this measure, it is less than or equal to this one, and that this measure, it is less than or equal to this one. In one direction, it is straightforward, okay? We don't have to do anything about it. We just want to show the other way around. I mean, we should show that this measure right here, it is greater than this measure right here, okay? In order to do so, we get a function phi in the space of function C1, which we know that it is a dense space in the space of function C0, okay, which we, of course, here we are understanding the measure as a function, a linear function defined over the space of functions of continuous functions, okay, which vanishing on the boundary. And then what we must do is to prove that for every phi in this space right here, which is greater than or equal to 0, we should show that this measure applied to this function, it is greater than or equal to this measure applied to the function phi, okay? This is what we should prove, okay? Very good. The argument, the approach to do it is to take this as a test function in the weak form of the approximated problem, which is going to give us this expression right here, okay? Then what we must do is to pass the limit in both sides when p converges to 1. When we do it, we have the limit of this expression, which is right here. We have the limit of this expression right here, which is going to give this expression right here, because we know that UP converges to U in the Lebesgue norm, and the gradient of UP divided by this expression, it weakly converges to Z with respect to L1, okay? And then we can use these two informations to reach that the limit of this, it is equal to this expression right here, okay? And then we send it to the other side of the equality in such a way that we have a minus here. To this, we just apply the usual Lebesgue convergence theorem, okay, in such a way that we have this expression right here. We know that the function U and the vector field Z, it does satisfy the equation in the sense of distribution, in such a way that we can substitute f of xu by the divergence of Z, okay? But this expression right here, it is exactly the way in which we define this distribution right here. And remember that this distribution is the object that generalizes the inner product between z and the gradient of u, okay? Then what we should do is, since we want to show that this is greater than or equal to this, what we must do is to show that this object right here, it is greater than or equal to this expression right here, okay? Then this is what we should prove. But this is exactly the statement of lemma 2.2 that I told you that it is the core of the paper, okay? And this we already know because we already have proved the lemma 2.2, okay? Then what we have got is a function u in a vector field z in such a way that the equation it is satisfied in the sense of distribution, the condition which says to us that z plays the role of what we have inside of the divergence of the mean curvature operator, it is satisfied, and we just it is just left to show that the boundary condition it is satisfied, okay? It is a very technical argument. I think that I should skip it. And also the last part of the paper, it is just to show that the function, it is really non-trivial, and it is based on some convergence that I think that I should also skip. And you can check in the paper if you want, okay? Okay, this is all that I have I would like to told you, and thank you very much.
Okay, thank you very much, Marcos, for your very nice talk. So now we open the turn for questions, comments. So if anyone has a question, please just ask directly to Professor Marcos Pimenta. Yes, João?
I'm sorry. First, Marcos, congratulations for your very nice talk. My question is very simple question, maybe. It's just about the limit of your sequence of solutions of the Laplacian problem. The function u, how do you prove this function is non-trivial?
Okay. Okay, how we should, okay. It is, okay, thank you very much by the question, João. This have about with the, okay, just make clear your question. Okay. You are asking me why the function u, which is the solution of the problem with the mean curvature operator, it is non-trivial?
Yeah.
Or okay, it
Yeah.
is right in that part of the. Okay, what we should do is to show that the energy of the function of the limit function, but I mean the energy of the energy defined in the space of function of bounded variation of the original problem of the original functional which is associated to the mean curvature operator, okay? We should show that the energy of this function, it is less than the energy of the trivial solution, okay? And we can use this, we can do it by using the geometry of the function f. I mean, exactly this condition right here, that is going, this condition right here. We can use this condition to say to us that the energy of the limit, it is less than the energy of the trivial function.
Okay, Marco, thank you very much.
Okay, you're welcome.
Okay, any other question or comment? Marcos, I have a couple of questions. My first question is related to the stability of this kind of solution. Is there any result about?
Okay, very good question. You mean, for example, if we consider the parabolic problem associated to it,
Exactly.
either or not, this solution is stable.
Exactly.
I have not investigated this sort of problem. I think that it is a very good question. And I mean, at least the reference that I'm used to, I have never saw this sort of result, but I'm sure that it can be found because I think that it is a very natural question.
Yeah.
Yeah.
And no result about stability of radial solution either, for instance? No, you don't know.
Yeah, I don't know. I don't know. Unfortunately, I don't know.
Yes, and my second question is related to how do you compute in practice numerically a solution for this kind of problem? Do you have an
I don't
idea?
have a clue. I don't know. I don't know. In fact, it is just a theoretical work. I don't know. I
Because
don't
it's
know.
not a constructive.
No. Yeah, the problem of this, it is just a different approach to deal with a problem which can be dealt by other approaches. And
Mhm.
I'm a little bit frustrated about this, the result itself, not because I think that it is a very nice result, it is a beautiful construction, it is from the purely mathematical point of view, it is a very nice procedure with generalized that something that we already knows very well that works through the one Laplacian. But in fact, I didn't succeed in solve this problem by this method in any situation in which the other methods still works. I
Mhm.
mean, I cannot, for example, give you an example of a problem with the mean curvature operator, which we cannot solve by the other problems, and we can solve through this problem right here. Yeah, I can give you this example.
Okay. Another question is you have this nonlinearity which depends only on you. Your method could also consider nonlinearity that also depend on the gradient of u.
By this method, it is not possible because you will, in general, you will lose the variational
Okay.
characterization of the problem. But for
Yes.
example, we
Mhm.
can apply this sort of approach whenever we have that the approximated problem has a weak solution in such a way that we get an estimate for the norm of the gradient of UP
Mhm.
without depending on P. We can apply this method whenever we have this. Then
Okay.
it doesn't matter whether or not the solution comes from a variational method or not. Then it is not something which is impeditive to the approach, I think.
Okay. Very good. So congratulations for your very nice talk. So thank you
Thank you
very
very
much.
much.
I just ask if is there any other